Hello and welcome to another video of the Grokking Decoding Interview series. In this video, we are starting a new pattern, which is the breadth first search. And the first problem we'll be looking at is the binary tree level order traversal. So the problem statement is as follows: given a binary tree, populate an array to represent its level by level traversal. You should populate the values of all nodes of each level from left to right in separate subarrays. So as an example, if we have this tree here, essentially we want to push the first level as a separate array, second level as a separate, and the third level as a separate array, iterating from left to right. And again, we have another example here. So things which we need to know here, essentially we want to use a data structure which is a queue in order to keep track of all the nodes for a specific level. In order to keep a track of all the nodes at a specific level. And once we have that sorted, we'll just have to push the results level by level into the result array. So let's quickly see how we can go about implementing a solution using queue. And at the end, we'll also be speaking about the runtime and space complexity of our implementation. So as the first step, if our tree is empty, we simply return the result. So we wouldn't be looking at anything else. As the first step, we want to go ahead and initialize a queue. We have already imported the construct from the queue. A couple of things which we need to know is if we want to, so queue actually imposes an important constraint, which is first in, first out. So whichever element you push into the queue first will get out of the queue first. And this will help us go ahead and do this level order traversal. So what we need to do is if we want to pop the leftmost element inside the queue, we have to use a pop left, which is already provided in the DQ construct. So, and we'll be using it to do the traversal. So just a quick heads up there on what functions of this data structure we'll be using. So like as the first step, we want to append the root node into the queue, and we have a while outer loop which will run until the queue is empty. So essentially what we are trying to do here is we want to push the root node into the queue. We'll get the size of the queue at that moment, and we'll iterate through the queue and start removing the leftmost elements for that length. Once we have already pushed this level into, say, a separate array, what we'll do is we'll simply get the left and the right child of this element and push it into the queue for next iteration of traversal. And we will continue to do it for all the nodes inside the tree. And this would give us the level order traversal which we are looking for. So let's quickly see how we can get that implementation here. So as the first step, I want to get the level size, which is the length of the queue. I also want to get the level nodes, which are all the nodes I will encounter in this level. And then I just want to iterate through all the elements in the queue. And pop, I just want to pop all the elements in the queue starting from the leftmost element. So I can get the current node, which will be the queue dot pop left, and I will append this into level nodes, the value of it. So the current node dot val If you see in the construct here, we do have a value parameter which holds the value for that node. And so once I have that in, I want to check if this node has a left child. So current node dot left. If it has a left child, then I just want to append it into the queue. Dot left, and if it has a right child, then I also want to append it into the queue. And once I'm over with this, I want to append the level nodes into the result. So what I'm essentially doing is all the nodes which I had in this level, I'm just appending it to the main result array which I have above. So let's quickly go through the implementation again, see if we understand it, and if we find any mistakes, we'll run it and see if the implementation is correct. And we'll also speak about the runtime and space complexity of the implementation. So we initialize a queue, we append the root, we iterate through the queue until the queue is empty. We have level sizes, level nodes. We pop the leftmost element from the queue for level size times. We have level size and level node. We pop the leftmost element from the queue, level size number of times. We append the value of the current each node into the level nodes. We see if they have left and right subtrees. If they do, we push it into the queue. And we append the level nodes into the result, and finally return the result. And this should give us the answer which we are looking for. Let's try to run it and see if this works out. 12, 7, 1, 9, 10, 5, 12, 7, 1, 9, 10, 5. Seems like it is working. Our implementation seems to be working. Let's quickly speak about the space-time complexity of this implementation. So runtime complexity O of n, we are traversing through all the nodes at least once. When it comes to space complexity, we have a queue, and this queue will go up storing at max the number of elements we can have at a single level. And we are also returning the result, which will contain all the nodes of that tree. So the space complexity worst case will be O of n is what I'm looking at. So let's quickly validate if our time and space complexity are right in this case. So we do have O of n when it comes to runtime complexity. When it comes to space complexity, it'll be O of n. We need to return a list containing the level order traversal. We will also need O of n space for the queue, since we have a maximum of n by 2 nodes at any level. Therefore, we will need O of n space to store them in the queue. Okay, so I hope you found the explanation clear. Please let me know in case there are questions. If something was not clear, more than happy to improve. And cannot wait to get on more medium and hard questions from the Traversal as well. Okay, until the next video, enjoy your day.